Hello and welcome to episode 3 of Molecular Mindset. I'm your host, Jake, and I'm a former high school chemistry teacher. And today we're going to be discussing the octet rule and another rule that you've probably never heard of, the duet rule. I had never heard about it until making this video. Now, before we get into all that, let's first talk about, I know you're coming for a test, so I'll hustle. But I want to talk about the particles. Now, in my first video that I know you watched, appreciate you. In my first video, we talked about the protons, the neutrons, and the electrons, subatomic particles that make up the atom, right? I'm sorry, and this isn't a diss. I mean no hate. I get worried calling people out on this channel because my channel has grown so much. My first video has, I think, 60 views, which I know it's a lot. It's a lot. My second video has 21 views. Oh, wow. Which is also a lot. In my comment section, you guys are requesting so many things, Q&As, all that stuff, and I'm going to try to get to it. I'm just busy, you know what I mean? But I appreciate all the love and support, okay? We're only going up from here. But no hate. Electrons are the MVP. Electrons drive all chemical reactions. Electrons dictate whether an element is, hey, what's up? I'm carbon. That was so cringy. Or if an element blows up in your face, okay? So electrons are the MVP. Protons, I got no hate. Protons are great players. They contribute a lot. And don't get me wrong, they have their moments. But at the end of the day, it's electrons. And I don't want to talk about neutrons. Enough said. No hate. But hate. So, you have two rules that we're going to talk about today. We're going to keep it simple. You have the first rule that I actually didn't know about until making this video. And that is called the duet rule. Okay? Now, before we get into what the duet rule is, let's talk about shells of electrons, right? So, to keep it simple, each atom has a number of shells that can hold electrons, okay? And these shells, to be happy, want to be full, okay? And what do I mean by happy? Happy means stable, okay? It means an element won't blow up in your face. Unhappy means kaboom in your face, okay? And there are plenty of elements that do that because the number of electrons that they have, and we'll get into that a little later. But to be happy means to be stable, and to be stable means to have a full shell of electrons, okay? Now, for this first example, I'm going to use hydrogen because hydrogen is the simplest element in the universe. It has an atomic number of 1, okay? Which means it has how many protons? You watched my first video. Nice. 1. If you got it wrong, click off, please. We don't want you here, okay? Or just go watch my first video. I should have said that. I apologize for the hostility. Hydrogen has an atomic number of 1, which means it has 1 proton, okay? Now, for the sake of simplicity in this video, we're going to assume if an element has a number of protons, it has the same number of electrons, so it's stable, okay? So if we have 5 protons, we're going to have 5 electrons, so it's stable. There's no charge, okay? So hydrogen, which we learned, though, it can have a different number of electrons, but for simplicity, we're going to assume it has the same number of electrons as protons. So hydrogen, if we look on the periodic table, it has an atomic number of 1, so we're going to assume it also has 1 electron, okay? And we know that that 1 electron is in the first shell, okay? Because it's in period 1, which we learned about in my second video. I think I talked about that. I hope I did. But it's in the first shell, which holds 2 electrons. So, happy equals stable, stable equals full shell. If our first shell can hold 2 electrons, and we only have 1, is hydrogen happy? No. Hydrogen is not happy. Little frowny face, I know, tragic. Hydrogen is not happy, which means hydrogen is not stable. It wants to react with something to get a full octet, or in this scenario, a duet. Now, let's break the word down. What does duet mean? Well, when I do a duet with someone, it's typically 2 people coming together to create music, or I think that's really all you use, duet. But duet just means 2, okay? So the duet rule, and I actually didn't know that this was a rule. I knew of the rule. I didn't know it had a name for it, kind of like octet. But duet just refers to 2 electrons in the first shell. So, the duet rule tells us that the first shell holds 2 electrons, so these 2 elements that have only 1 shell want 2 electrons. Now let's get into the, what do people say? It's that boomer saying, the meat and potatoes. Let's get into the meat and potatoes of this. The octet rule. And this is all going to make sense. I know this is a lot being thrown at you, but just give it some time. The octet rule tells us the same thing as the duet rule. How many electrons atoms want. Now we know that hydrogen and helium are the only atoms, and let me make that very clear. Hydrogen and helium are the only atoms that follow the duet rule. They only want 2 electrons in their outer shell because they only have one shell. And that one shell, that first shell, only holds 2 electrons. Okay? The octet rule tells us something different. If we break the word down, oct refers to what? Well, an octopus has 8 tentacles. An octagon has 8 sides, for all my UFC fans. Octane has 8 carbons in it. Yeah, you got the gist. Oct means 8. Okay? So atoms follow the octet rule. Okay? And we're just going to focus on the next 2, the second and third period. So lithium, beryllium, sodium, magnesium. We're not going to worry about the rest because it kind of gets a little fuzzy with orbitals and stuff. We're just doing the basics. Okay? Octet rule refers to 8. That's how many electrons atoms in the second and third period want to be happy, to be stable. Okay? Remember, we're all about stability and happiness. Okay? So they want 8 electrons in their outer shell. And we know that our first shell holds how many? So like with hydrogen and helium, our first shell holds 2 electrons. Okay? Holds 2 electrons. Our second holds 8. Octet. They want 8 to be happy. Remember, we want full shells to be happy. And our third shell also holds 8. Okay? Like I said, when you get down lower, it gets a little weird. We're not going to talk about that. Okay? So our first shell holds 2 electrons, like hydrogen and helium. Our second shell holds 8, and our third shell also holds 8. Okay? So, for example, let's take an element. Let's start working with it, because I know this is very confusing. This is a lot. Let's actually start doing examples so we can understand what's going on. Okay? So, let's take an easy one. Lithium. Okay? Lithium has an atomic number of 3. Okay? So it has 3 protons. And we're also going to assume, like I said earlier, that it has 3 electrons. Okay? So, sorry, my mic died for some reason. So lithium has 3 protons. We're going to assume, like I said earlier, it has 3 electrons. Okay? Now, lithium, we're just going to go one by one, right? Lithium has the number of shells that it needs to take these electrons and start filling them. Okay? So, for example, we have 3 electrons. How many go in the first shell of lithium? So we'll draw lithium down here. How many go in that first shell? Well, 2. Okay? So let's draw 2. Now, I've used 2, right, in that first shell, because we know the first shell can hold 2 electrons, and I have 3. So I have enough to fill this first shell. So that's 2. Okay? Now, out of my 3, I've already used 2. So how many do I have left? I really hope you can do that math. Thank you. Sorry, that was rude, but come on. So we've used 2, and we have 3. We can use 1 more. Okay? And we know that our second shell wants 8 to be what? To be happy. How many do I have in our second shell? We got 2 in our first shell. First shell wants 2, so that's full, so that's happy. But then, in our second shell, we only have 1, but we want 8. Lithium is not happy. Okay? Lithium is not a happy element when it's stable. Okay? Now, like I said earlier, it can bond with other atoms, which is a whole nother video. It can bond with other atoms to be happy. And we'll talk about that, like I said, in another video. But by itself, it is not a happy atom. And actually, funny enough, you can watch videos. Lithium is super, super explosive when it comes into contact with water. You may have heard lithium-ion batteries. Don't open those up and get them wet, because they will cause a fire that you cannot put out with just water, because it reacts more underwater. So you think, oh, let me just pour a glass on it, right? You'll make it worse, okay? So lithium is actually super, super reactive because it wants so badly to get rid of that 1 electron, okay? And this goes into another rule. So our octet rule says that we need to have 8 in the second shell. We only have 1 here, okay? So lithium wants to do what? It wants to either gain 7 to become happy, right? It just wants a full outer shell. That's all it wants, is a full outer shell. So it could either gain 7 to fill that second shell, gain 7, or to have a completely full outer first shell, it could lose 1. Okay? So, would you rather gain 7 or lose 1? Would you rather have to make $7 million or lose $1 million? That's maybe a bad example. But would you rather have to run 7 miles or That's also a bad example. You get what I mean, okay? It's easier to lose 1 electron than it is to gain 7. So what lithium's going to do is it's going to give up its electron so it can have a full outer shell, okay? Because all it wants is an outer shell, whether that's a full second shell, a full first shell, a full third shell, a full eighth shell. It doesn't matter. It wants a full outer shell, okay? Let's do another practice problem. So let's take nitrogen. Nitrogen has an atomic number of 7, which we're going to assume it has 7 electrons. So 7, meaning 7 electrons. Okay, so let's do the rule. In our first shell, we can hold how many electrons? 2 electrons. So let's draw them out. 1 electron, 2 electron. Now, we started with 7, right? So now, 7 minus 2 is 5. We have 5 more. So 1, 2, 3, 4, 5. Is nitrogen happy by itself? Your answer should be no, right? Our second shell wants to have 8 to be happy. It needs 8 to be happy, okay? Nitrogen alone only has 5 electrons in its second shell. So if it wants 8, it needs 8 to be happy, and it only has 5, it is not happy, it's not stable. It's going to react with other atoms to get what it wants. Now, nitrogen can either gain 3 or lose 5. So what's it going to do? What's easier? Gain 3 or lose 5? Well, gain 3, right? It's really just the number that's smaller. It's easier for nitrogen to gain 3 than it is to lose 5. So in the world, nitrogen commonly reacts with other nitrogen and bonds with it covalently, which we'll talk about in another video, to kind of gain, covalently bond. That's a bad example, but we'll talk about that in another video. But it would rather gain 3 than lose 5, okay? Now I'm going to get rid, well, we'll do one more practice. Let's do aluminium, because I'm British. Aluminium. Aluminium has an atomic number of 13, which means we're going to assume it has 13 electrons, okay? Now, let's draw aluminium down here. Aluminum, in its first shell, has 13 electrons, and we only need 2 in the first shell, so that can easily accommodate that. Okay, so 2 in the first shell. How many are going to be in our second shell? Well, 13 minus 2 is 11, and how many fit in the second shell? 8. So we can easily accommodate 8. 1, 2, 3, 4, 5, 6, 7, 8. So now we have 8 in our second shell. Our second shell's happy. It's full, right? It can hold 8. It has 8. Second shell's chilling. Bing chilling. But now in our third shell, it also wants 8. But we used 2 in our first shell, plus 8 in our second shell. We've used 10 out of our 13 electrons. So how many can we fit in our third shell? Only 3. Sorry, I'm getting over a cold, so I'm still stuffed up. We want 8 in our third. We only have 3 because we had 2 in our first shell, 8 in our second, which is 10. We only have 13 total because it's 13th on the periodic table. We're kind of screwed, right? So is aluminium happy? No, not happy. Frown face. Not happy. Aluminum is going to bond with other atoms to either gain or lose electrons to fill this outer shell. Now, is it easier to gain 5 or lose 3? Gain 5, lose 3. Lose 3, right? Does that happen every time? No, sometimes different reactions call for different things. But that's just kind of a rule of thumb is, you know, if it's easier to gain 2, well, it's probably going to gain 2. If it's easier to lose 3, it's probably going to lose 3, right? But there's different chemical reactions all the time, okay? So I don't want to speak in the absolute there. So now I want to teach you kind of something cool, something I didn't know for a while, and it frustrated me because I didn't learn it till later on. I'm not going to tell you how old I was when I learned it, but I finally learned it, and I was like, oh, that makes a lot of sense. I think I was in high school. But we've all heard of noble gases, right? Noble gases. What the heck is a noble gas? Why is it called a noble gas? We know, if you might not know, which is fine, but some people know that the right group on the periodic table are the noble gases. So you have helium, neon, argon, krypton, xenon, radon, and oganesson. Okay? Oganesson is grayed out. I don't know why. Doesn't matter. But the main ones are helium, neon, argon. Okay? Let's use argon. Actually, let's do neon. Ne. Neon is number 10 on the periodic table, so we're going to assume it has 10 electrons. Okay? Now, neon, in the first shell, this is a little test as well. How many electrons go in the first shell? 2. Nice job. Proud of you. Pat on the back. 2 in the first shell. So, neon started with 10. It used 2 for the first shell, so it has 8 left. You might see where this is going. This is pretty cool. Second shell can hold how many electrons? You've learned nothing. 8. 1, 2, 3, 4, 5, 6, 7, 8. 8. And we have 8 left. So, neon has a full outer shell. What did we learn just 5 minutes ago about full outer shells? Full outer shells are what make atoms happy. This is why they're called the noble gases. Their outer shell is full. They are complete. They are one. They have no reason to react, which is why they don't react. These gases are stable. You can still break them apart, but you have to input a ton of energy to break them apart because they're happy. They're chilling. Okay? And what's kind of a cool side story, I worked in a research lab, a medicinal chemistry research lab during my undergrad, and we were putting argon in our reaction vessels, in our round bottom flasks with our reactions. And at first I was like, why are we putting argon? But it makes total sense. Argon doesn't react with anything. Why would I put in a bunch of oxygen, O2, an atmosphere that with a bunch of other crap that could react with my reaction? I want my reaction to be pure. I want my reaction to be my reaction. I don't want it to be a bunch of other crap. So we would pump argon into it with these big tanks because argon's not going to react with it. Argon's going to still keep the vessel pressurized, but it's not going to react with anything, which I thought was super, super cool. Argon is a noble gas, just like neon, helium, krypton, so on and so on. Okay? One last thing before I let you go, you loser. I don't know why I called you that. That was really uncalled for. I apologize. I'm the one in my apartment talking to myself, talking to a camera about chemistry because I'm a nerd loser. Don't throw rocks from a glass house. That's the lesson of this video. So, awkward. One last thing before I let you go. Let's pick oxygen. Oxygen is number 8 on the periodic table, which means it has 8 electrons, typically. Not always, but for the sake of this video, we're going to assume. So, oxygen, that's kind of a bad example because that's... Okay, let's get our mind out of the gutters. 2 electrons. I shouldn't pick that because that looks like an electron shell, but it's not. Oxygen on the first shell has 2 electrons, okay? Now, on the second shell, it wants 8, right? But we've already used 2 of our 8. So we have 6 left. But it wants 8. 1, 2, 3, 4, 5, 6. So there's 8 electrons total. 2 in the first shell, 6 in the second. It wants 8 in the second, as we've learned. Is oxygen happy? No. But what I want to tell you is, what do we call these electrons on the outer shell that are not fulfilling the octet rule? Okay? So they're not filling the full shell. It's 6 out of 8. What do we call these? We call these valence electrons. And you're going to hear valence a lot. Valence just tells you that an atom has electrons on the outer shell that are unbonded. They're not bonded. They're not filling up the outer shell. Okay? So not necessarily not bonded, but they're not filling up the outer shell. Okay? Which is why we have chemical reactions. Remember I said at the start of the video, electrons are the MVP. They drive all chemical reactions because... Ooh, awkward. They drive all chemical reactions because atoms want to be stable. They want a full outer shell. Okay? So, what I want you guys to do on this last one, these are valence electrons, as I just said. Sorry, that was an alarm that went off. Last one that I want you to do is I want you to tell me if silicon, which is number 14 on the periodic table, which has 14 electrons, is happy, and how many electrons are in each shell. Okay? So pause the video. Do this really quick in your notebook. I hope at least one of you is doing it in your notebook. Probably not, because I'm a loser. Sorry. Silicon. Pause it. Go. Draw it. And we're back. Okay. So we have 14 electrons. First shell we know holds 2 electrons. Second shell we know holds 8, 2, 3, 4, 5, 6, 7, 8. We have 14. We've used 10, so we have 4 left. So that means in our third shell, we have 4 electrons. Now, a couple questions for you. Is silicon happy? No, it is not happy because it wants a full outer shell. It only has 4, and it wants 8 in that outer shell. It is not happy. Now, another question that we just learned about. How many valence electrons does silicon have? You may be inclined to say 14 or You might think 12 because the second shell has 8 and the third shell has 4. But remember, the valence electrons are only electrons on the outer shell that are not full. Okay? I said unbonded earlier. Don't worry about that. The outer shell that's not full. So does the second shell have any valence electrons? No, because it's full. Does the first shell? No, it's full. Does the third shell? Your answer should be yes, because it has only 4 electrons. It's not filling the shell. Therefore, they are valence electrons. And these are the electrons that bond with other atoms, okay, because they want to become happy. I know that was a lot. I hope that helped. I really want these videos to kind of have a style of, like, I don't have a script. I don't have a prompt I'm reading off of. I miss the act of just getting up in front of a classroom and just kind of not winging it. Like, you go in with previous thoughts of, like, I want to do this that way. But I really enjoyed the art of anything can change. I get up. I've done this take like 4 times because I had stuff in the background go off, other stuff. I had it so the board, you couldn't read it because it was flipped. I know I'm an idiot. I'm a loser. I get it. Don't want to hear it. But I love each time it's different. So I know it's fast. I know it's a lot. But I hope you kind of like these impromptu, if you will, videos. Not that I'm not putting a lot of work into them, but like, I don't know. I just love the thrill of getting up in front of a classroom or a camera and just going for it. Each take's different. Each time I make different jokes, make different analogies, all that good stuff. So I hope you enjoyed. I hope this helps on your test. Go ace it tomorrow morning because I know it's like 2 a.m. and you're cramming. You got this. Take care. And bye-bye. I really appreciate all your comments in the comment section. No one's probably watching this, but I appreciate you. So thank you. Goodbye. Awkward. Oh my god, I didn't mean to hit record again!